Shall we start, ma'am?
Sir, we can start.
Thank you. So, on behalf of Kunglad College of Engineering Technology, I welcome all. Session 2 on the topic of analog signal processing in VLSI. I welcome you all the participants. It's pleasure to welcome our resource person. It's pleasure to welcome our today's resource person, Dr. V. Geeta, Associate Professor, Department of VCE, Kongu Engineering College, Erode, for the topic of role of analog signal processing in VLSI. Welcome you, ma'am.
Thank you, sir.
Okay. I request Gautam to give short intro about our resource person.
Good afternoon to all participants who are gathered here. It's my warm welcome to our resource person, Dr. V. Geeta, Department of Electronics and Communication Engineering. Every thought you produce, anything you do, it bears your signature. Likewise, she completed her master degree in VLSI design from Kongu College of Engineering College, and she completed PhD in Engineering College, Information and Communication Engineering in Kongu Engineering College under Anna University, Chennai. Her area of specialization in VLSI design. She has 13 years of teaching experience, and she published more than 15 papers in national conferences and 7 papers in international conferences. She published a paper in 11 journals in national and international conferences. In this way, I would like to hand over this session to our resource person, Dr. V. Geeta, to enrich our knowledge.
Thank you. Hope I am audible.
Ma'am?
Am I audible?
Yes, ma'am, audible, ma'am. You can share your slide, ma'am.
Okay. Is the screen visible?
Yes, ma'am, visible, ma'am.
Okay, thank you. Good afternoon, one and all. So I am Geeta, Associate Professor from Department of ECE, Kongu Engineering College. I am very happy to be here to share the knowledge with you in the field of analog signal processing. So in this session, we are going to discuss about the role of analog signal processing in VLSI and its strengths and challenges. So in today's presentation, we are going to share the basics of analog IC design. So is analog VLSI design is dead, and what is VLSI microelectronics, then mixed signal VLSI chips, what are all the analog building blocks, then challenges, what are the current design tools available, then we are going to discuss about the reasons for failure of analog designs and what are all the testability methods for analog circuits, then CAD tools for analog design, then what are all the VLSI technology trends. So based on the discussion with all these related topics, we are going to conclude something related with the research issues. So I hope most of the participants are from VLSI domain, and in VLSI domain, most of our focus is towards digital VLSI. So me too new to analog domain, but we started working in the field of analog VLSI. So I hope this will give some introduction, and this will be an eye-opener session for the researchers to be analog VLSI designer. So with this intro, we will do the session. So actually, before 1970s, all the electronic circuits were designed almost using analog design techniques only with the discrete components. But with the development of integrated circuits, digital circuits become basis of many systems, and because of this, analog IC's development is little bit slower, not little bit, much slower when compared with the digital ICs. We all know the advantages of digital system because of its speed, accuracy, easy design, then versatile nature. Digital design takes more development when compared with the analog ICs. So here we will see what is analog IC design and what is the current position, current scenario in this analog IC design, and what are all the challenges. So here, analog IC design means this is a implementation of analog circuits and systems by means of IC technology. So when going for VLSI, whether VLSI is digital or analog means, in today's scenario, it is the combination of both digital and analog on a single chip. When moving towards the submicron structures, many of the applications are with the combination of digital and analog circuits on a single chip. So what are all the challenges in VLSI design? Either it is analog or digital. Common challenges in VLSI design includes the power dissipation and the leakage power management, then short channel effects in deep submicron transistors, then noise because of capacitive and inductive nature of interconnects, then the problems related with the integration. So what are all the difficulties in the analog design domain? So when going for analog, we know digital is zeros and ones, whereas analog is continuous. So because of this continuous nature, we need to consider more parameters into account while going for designing. So the parameters that should be considered for analog circuit design includes temperature, noise, and power signals. So these parameters can affect the analog circuits. So we have to consider all these parameters while going for analog design. So this is the process technology evolution. So in 1960s, the ICs includes only 2 transistors, whereas in 2000, this includes millions of transistors. So we can just able to understand how the process technology is developing day by day. So as VLSI engineers, we are all familiar with Moore's law. So in 1965, Moore's law, we know Moore's law is for every 18 months, the number of transistors in ICs doubles, right? So here, the first graphical representation is in 90s, the number of transistors. So it is in tens up to 1975. Whereas in today's scenario, up to 2000, the number of transistors increases to millions. So how the number of transistors doubles, right? So you can just see the numbers, how this varies. In 1975, this is in 2000. So yes, analog VLSI design departed or dead. So here, actually this is not true. So if we are going for the data available, the analog chip sales for 2002, it is $39 billion, whereas in 2004, it is $48 billion. So you can see the difference. 39 billions in 2002, whereas $48 billion in 2004. It goes on increasing only. But what is the problem? Why analog design is not that much popular is actually when working with most of the system, we know the real-time signals are analog nature, and most of the transducer outputs are analog in nature. So when going for designing a system, a small percentage of the total chip is analog means there the analog component decides the overall system performance, even though it is with the small percentage of contribution in the total chip. So in practice, pure analog system is not at all possible. So here, majority of the system are integrated with the digital domain. So here, what is important is the designer should know both analog and digital circuits. He should able to understand the design, and the interaction between the two domains is important. The designer should understand the interaction between the two domains. So this is what is behind analog VLSI design. So here most of the real-time signals are analog, and even the analog part is small in nature. The overall system performance is affected. So as we already discussed, before 1970s, pure analog design techniques were followed with the discrete components. But when coming to the development of digital system, most of the systems are moved towards digital. So this digital IC development is good when compared with the analog ICs. So in the earlier days, hybrid, bipolar, single channel MOS technologies were developed, and later, as per the market demand, the silicon VLSI technology advancement is happened. So here, the ultimate goal is to develop a system on chip with mixed analog and digital circuitry. As we already discussed, the pure analog system is not in practice. The designer should know both digital and analog, and the mixed analog and digital circuitry on a system, on a chip, is the ultimate goal. So recent trend is scaled CMOS and bi-CMOS. So in CMOS, both N-channel and P-channel MOS devices are fabricated on the same substrate. Here, bipolar and MOS devices on the same substrate. So they can get the advantages of both bipolar and MOS device together. That is the advantage. So VLSI microelectronics is interdisciplinary. So here, because of this interdisciplinary effort, whatever may be the new technology, many innovative applications are possible from this VLSI domain. So if one want to work on any one field, the knowledge of the other interdisciplinary field is also must, because this is a combination of different fields. So the knowledge in one field is not sufficient for a designer. He should be able to understand what happened when we are going for the when we are moving towards the combination of different fields. So here the designer should have sufficient knowledge about CAD tools. This is also one of the basic need. So when going for building a circuit, what are all the optimization techniques and algorithms available with the CAD tools? This is one of the important need. So here, when working in the VLSI field, one should have the sufficient knowledge in CAD tools and also the device design. So these are all the components of VLSI microelectronics. So inputs from the material research, then VLSI circuit and system design using CAD tools and the simulation tools, and from device modeling. The system can get inputs through all these fields, and we can develop the application circuits related with all the domains for specific applications and in the communication field. And there is possibility for technology development using these inputs. These are all the components. So here analog VLSI signal processing has two general, normally in signal processing, as we already discussed, the combination of both analog and digital on the same chip, right? So here the two general categories of signal processing includes mixed analog digital, mixed digital analog. So these are the two categories of signal processing systems. So this is just seems to be same terminology, but these are different. Mixed analog digital, this is mixed digital analog. So here this classification is with respect to the roles on analog or digital they play on the chip. So the first one, mixed analog digital. So here the analog part provides the I/O interface to the core of the chip, which is digital. So the first one represents I/O interface. The second one represents core of the chip. So here, along with the data converters, the interface circuits, etc., which are analog, they can be connected with the digital core. Again, from the digital core, we can get the output through the analog interface. So here, these data converters, amplifiers, filters, compressors, power drivers, sensor interfaces, all these analog components are at the periphery of the chip, right? So the core is digital. Even though these components are at the periphery, these are playing the major role in the overall system. So here we are going to see an example with the help of this diagram. You can able to understand what mixed analog and digital means. See here, the transmitter, a pulse generator, and oversampled D2A converter, a filter, driver, then adaptive hybrid balance, again a filter, then a tone detector, then control, again a to D converter. So here, along with all the data converters, the AFE, which is analog front end of the U interface transceiver in an integrated standard digital network. So this example is AFE of U interface transceiver. So here this interface is the final link between digital world of this integrated standard digital network and the end user. So whatever may be the data processed in the core, all the peripheral components are analog. The core is digital. So you can see all the filters, drivers, converters, data converters, digital to analog, analog to digital, everything. So here, this analog components plays the major role. So by means of this AFE, we can able to achieve higher immunity to noise, and we can get highest baud rate. So the system will be speed, and non-linear echo cancellation is possible. Then the second one is mixed digital analog As we already discussed, the first part represents the I/O and the second part represents the core. So the digital part provides the input-output interface to the core analog. Right? So here, with the traditional mixed analog digital, this can interchange the digital and analog. So this is the emerging trend, mixed digital analog. So the I/O part is digital and the core is analog. So conventional system is analog I/O and core digital. So this is just an interchange between the analog and digital, which is the emerging trend. So many neural systems are based on these models only. So if we go for pure analog systems, then that should comes under this category only, mixed digital analog. Pure analog systems comes under this category. So here, the advantage is we are using digital part for I/O, right? So because of this digital part, the complexity with the input output is easily handled. That is a major advantage of mixed digital and analog system. So this is one of the example for mixed digital analog. So here from the digital we are getting input and all the processing are analog nature. So the digital input, then D2A conversion, analog signal processing, so analog core, then the output is analog nature, so again A to D converter, then it is processed and it provides the output. So the input and output both are digital. So from the digital, for analog system we need D2A converter, we need analog input, so there is a converter. Then output from the analog is analog nature, but we need the output in digital. So here again we are using A to D converter and the external output is available. So this is one of the example for mixed digital analog system. So here 2 micrometer scalable process, an example with 3.2 billion connections. You just imagine this is a neural based vector quantizer chip. This is a photography of die from IEEE standard 1992. So you can see synapse matrix. This is neural based vector quantizer chip. So these are synapse matrix, digital encoder, and this is WTA, winner take all cells, then a column decoder, row decoder, and the IO pads are given here. So this is a die photography of a neural based vector quantizer chip. So 2 micrometer scalable process is used, the capability of 3.2 billion connections. So the next one is just a comparison between analog VLSI and digital VLSI in terms of cost, power, and computational density. So here this MCS represents million connection updates per second, and million connections updates per second. In terms of MCS it is given. So here the first one is for conventional digital, then special purpose digital, then dedicated digital, then this is dedicated analog, the last one, right? So here human brain cost is separately given. We are not bothering about that. But when doing comparison with the dedicated digital and dedicated analog, you can see a vast difference among the cost, power, and computation density, which shows analog VLSI is superior to digital in terms of cost, power, and computation. This is again from Byte 1992 datasheet. So what are all the analog building blocks? So current sources, current mirrors, single stage amplifiers, differential amplifiers and op-amps, comparators, voltage references, data converters, then switched capacitor circuits are all the analog building blocks. So all the things are familiar to us. So we know all the fundamentals, but how to use this for our application part is important while going for the design. So here, what are all the analog challenges? So here, signaling speed is very important. So normally it is to the maximum of 5 gigabits per second. Then the complexity is the next problem. So when working with the advanced analog design, the complexity is more, and the analog designers often use interface chips. For example, Texas Instruments LVDS. So this is low voltage differential signaling repeater. So this is built-in pre-emphasis on the transmitter side and equalization on the receiver side. So this is useful for the analog designers when we are going for interface chips. Then the main aim is to minimize power and silicon die area. So speed is the major problem. So it is the maximum range is 5 Gbps. Then the analog design complexity when working with the advanced design. Then the material for the PCB, what is used is very important. Then when going for interfacing many chips, we face the difficulty. Then what are all the methods to minimize the power and the silicon die area is the next challenging aspect. Then when signal speed increases, automatically the clock and timing should be reduced. So here, when working with the PCB layout is the last step in the design process. So PCB layout is the last step in the design process, but it is very important. This is like the location in the real estate business, where to place the chip on the board. That is very important. So if we are locating the components at far distances, then the connecting wires and the thickness of the copper wires, then far distance effects may cause problem. If we are keeping the components closer, that may be advantageous for few, and that may also cause few problems. So the place where to locate the chip on the board is very important. So for the decision making towards this, many of the IC suppliers verify the data sheets given by the supplier. Many designers refer the supplier's data sheets for proper integration, and this may again gives the problem in finding out faults. So here, this is a WebBench designer tool, which includes some algorithms, software algorithms. So for easy design and to minimize or to do power analysis, we can use these tools. So this is one of the tool where we can simulate and we can do the analysis part, and we can change the materials, and we can take the schematic and all the analysis report by means of using this tool. So the Texas Instruments and the National Semiconductor both combine together and provide many of the tools for analog designers. One is WebBench Designer. So within seconds, this can provide all the possible calculations related with the power and sensors, whether they can meet the designer's requirement. And by means of using this tool, we can able to make the value-based comparisons before going for design. So the main objective of the tool is it should provide more visual, and it is easy to use, and this provides more intuitive calculations. So here, by means of selecting and arranging the components on the breadboard, we can use this WebBench designer for analog design. So this can integrate both the existing tools and the new tools, what are all emerging in today's scenario. So without these tools, the designer can spend weeks or even months of times to customize their design, but using this we can do the analysis within minutes and seconds. It is possible with the software tools available. So here, from IP to prototype and test to writing system algorithms, the designers feel difficulty in the simplification of development cycle and production cycle for critical applications. So here, the Texas Instruments and the National Sensor analog front-end system and ICs offer the integrated hardware and software development platform. So the designer can quickly create a design online, configure it for their requirements, and rapidly they can prototype it. It is possible by means of the tool available. So for simple calculations like the input signal common mode range, the instrumentation amplifier, common mode voltage calculator which is introduced by the Texas instrument is useful, and by means of using this calculator, the designer can do design within minutes. So by means of using this type of calculators, we can solve many of the problems which are expected during the design. By means of simple spreadsheet calculator like this, we can avoid the problems during design. So here, Analog Devices has improved some website in order to help the design engineers. So one of the tool is Engineer Zone. So this is a technical support for analog designers. So this company, Analog Devices, can offer these tools for analog engineers in order to calculate the gain, noise figure, then third order intercept point, gain compression, and power calculation. So by means of switching the calculators between the transmitters and the receiver modes, one can able to calculate all the referral values then and there. The user can switch the modes between the transmitter and the receiver and can do the analysis. So the next one is circuits from the lab. So there is a list with the proven reference designs. So if the designer want to refer them, then they can take from the circuits from the lab. So they may be having confidence over their design. So with all these design tools and challenges, what are the reasons for failure of analog design? So here, the main reason is analog circuitry stopped following Moore's law, but that has not always helped. There is a large gap between analog and digital dependability. So if we are referring so many result analysis, most test failures are related with the analog part when compared with the digital part of any system. So most of the test failures are with the analog system, because the analog design and analog verification part uses older methods for doing that, and the automation and verification methods for analog design is also lagged. So from Siemens Business Mentor, we can get the statement like this: the analog blocks do account for a large percent of chip failures. So the major cause is chip failure, and this is due to high complexity, error-prone process, then full custom design, then variability, limited systematic verification to access robustness, then much less automation compared to its digital counterpart. So normally analog systems are complex and there are more possibility for occurrence of error during processing, and it is full custom design, then variability, then verification, systematic verification is limited, then automation is less when compared with the digital part. So we will see what are all the testability modes, testing modes available for analog VLSI circuits. So here for analog VLSI circuits and internal circuit nodes, in order to find out the fault, we need testing. So here analog testing, digital testing, and mixed signal testing. So for example, analog testing means everything, the input, output, and the core should be analog. This is pure analog. So in the same way, if the input, output, and the core all are digital, then that comes under digital testing. So if we are going for mixed signal VLSI, you can say the input is digital. Then from digital, it is converted to analog and it is given to the analog core. Then it process and the output is analog. So from analog, it should be converted to digital, again a converter, and the digital should be given to the digital core, from where we can get the output as digital. So here, this is mixed signal analog and digital. So mixed signal VLSI. So we need to do testing for this also, mixed signal VLSI, and also for the pure analog and digital. So here in the DFT, while doing comparison between digital and analog, for digital there are different DFTs, macro test, boundary scan technique, self-test, and many more number of tests are available for digital. For analog, there are more number of approaches. So the testing with the catastrophic fault, so this is just similar to your digital circuit faults. Then ad hoc test approaches and new approaches with the CAD tools. So all these are possible for analog circuits and also for digital circuits. So fault modeling and simulation is one of the important thing. So physical fault means there may be pinhole in oxide layer or unacceptable change in the doping concentration. Fault on hole means this may affect the entire behavior of the circuit. So the fault may be a minor fault, but the combination of many minor faults may combine together and leads to failure of the system. So the two basic fault categories are hard fault and soft fault. So catastrophic faults are hard faults, and the parametric and deviation faults are called soft faults. So what are hard faults and what are soft faults? So the catastrophic faults are dominant, and these are occurring due to structural deformation. If there are presence of large dust particle, then that may end with a hard fault. So example for hard fault includes open and short interconnection. So if a terminal is open, you are able to understand what happened to the device. If there is short, then what happened to the device. So you can say stuck at, stuck open, stuck on faults are examples for catastrophic fault. Then parametric and deviation faults are soft faults. but these are very difficult to identify. So if there are minute dust particles on the wafer, then it is difficult to identify, and those comes under the category falls due to tiny particles, comes under the category of soft fault. Then multiple faults, non-catastrophic errors, or other faults available with this. So in order to detect the above said faults, we can go for simulation tools. So when working with the fault model, we need input test pattern. So by means of providing the input test pattern, we can calculate the fault coverage. So here the deviation faults are again classified into global and local deviation faults. And for mixed signal circuits, the simulators available in recent scenario includes SMASH, SABER, featuring macro modeling and Monte Carlo analysis. So these are the recent development in the mixed signal simulators. So here the testability analysis technique. So we need to improve the controllability and observability. So for testing of analog or mixed circuit, we need to provide some testing nodes. So the analog circuits normally exhibit multiple deviation faults. For example, you can say rank test algorithm. Rank test algorithm means between the measurements, by means of finding out the relationship, the equation, the relationship can be expressed in the form of equations, and by means of analyzing the functional behavior of the circuit, one can able to find out the fault. So here the functional unit of analog circuits can be tested. For example, you can take RLC circuit, where we can able to do the testing over the functional block by means of providing test points. So here P1 and P2 are the two test points incorporated, two test nodes you can say. So here by means of using this test node P2, see here we can able to measure the resistance value, and by means of using the node P1, we can able to measure the value like this, the dotted line. So we can able to find out the change in value. So we can able to test what is the output from this node and what is the output when the same input is given through this inductor. So what is the expected input and what is the expected output across the two test points? We can able to measure this. So there are ad hoc methods, and what are all the general guidelines? So two fundamental approaches towards testable design. So here this approach starts immediately at the beginning of any design. So here in the ad hoc approach, we are adding probe point. So by means of adding a probe point, even if the chip is already manufactured, we can add a probe point. So what happens when probe point is included? That should occupy more area, right? So more area By means of adding probe, the node resistance increases and there is need for buffering. But the advantage is just we are going to add a probe point. So this is fast and cheap. But the drawback is it occupies more area, which increases the node capacitance. Then the second approach is a hierarchical approach, which is called macro testing. So macro testing means that partitioning of the complex circuit into different functional modules. So here, for example, op-amp with the two resistors R1 and R2, and we are providing input. So for this circuit, we are going to measure few parameters like closed loop voltage gain, conductance, and offset voltage, slew rate, all the things. But here, by means of using this formula and by means of accessing the nodes N1 and N3, here node N2 and N4. So by means of measuring this N1 and N2 and N4, we can able to calculate all these parameters. So partitioning a complex chip into different functional modules is called macro testing. So by means of partitioning into simple circuits, the testing is possible. So which is macro testing. So here the drawback is the observability, controllability, and isolation in order to carry out these tests. So by macro testing, we are unable to get good observability and controllability. So obtaining these is not comparatively good when compared with the ad hoc approach, where we are providing probe for testing. So by means of keeping probe, we can get good observability and controllability. So here, in order to increase the observability, one can add test points. So the first thing, if you want to increase observability, so what is the output from the particular node? So how easily one can observe the output, right? That is the meaning for to increase in observability. So how easily we can able to observe the output in between the circuits. So we can add test point, or we can combine test point, or we can use micro probes, or we can use built-in switches, right? So here, when using micro probes that may be connected with the CAD database, or we can probe physically. So the drawback is, again, when we are working with the probe, that increases the area and node capacitance. Then here another drawback is impedance mismatch is possible. Then when working with the probe, we are physically connecting the probe and disconnecting the probe, right? So there may be possibility for mechanical damage. If there is mechanical damage, then that can lead to crosstalk. If we are using built-in switches, then switches are built within the chip. So you can say the hardware is more and there is need for control signals in order to work on the switches. So the design time is more. So this is the example. So in the circuit, you can see the switches, inbuilt switches. So by means of working with these switches, we can able to get the outputs. So the observability is good, but by means of including switches, the hardware increases. That is a major problem. So in the similar way, if you want to increase the controllability, then the input to be isolated from the output of the previous stage. So controllability means how easy, how easily the designer can control the output by means of providing some input, how easily he can get the required output. So if you are working with some gates, for example, if you are providing one, you know what is output from the particular gate. So if you want to check the gate, how easily you can force the input and how easily you can get the output. So how the control of the circuit is possible. So here also we can do this by means of adding probe point. So here another one is using laser beam. So most comfort method is using gates and analog multiplexers. By means of multiplexers and analog multiplexers and gates, we are able to provide the input. So if you want to give 0 or 1 by means of the control signal through the mux, you can force the zeros and ones. In the similar way, you can control the output. So advantages when working with the gates and multiplexers, we can able to disconnect the input from the previous stage. So the isolation between the input and output is quite good. So here the destructive method is we can remove metal layers. So here this is a mechanical or chemical method. So if we want to break or restore the feedback loop, we can go for the options with analog switches. So this is the other method for breaking or restoring the feedback loop. The next technique is scan technique. So in the digital world, the scanning techniques are the most used design for testing. There are a number of approaches available. So the basic approach is connecting the node to the shift register. So if we connect it to the shift register, we can increase observability and controllability. When we are including shift registers for the purpose of testing, then we need additional input and output pins. So here when shift registers are included, the size will be larger and the testing takes more time. So here for example, you can use oscilloscopes instead of shift registers. When working with the digital, you can say shift registers. In analog case, you can just use oscilloscopes to monitor the output. So here the well-known approaches of analog shift registers are bucket brigade-like devices and charge-coupled devices. So these are the two well-known approaches when working with analog shift registers. So the next one is analog computer-aided design. So it performs two different tasks actually. One is circuit design task, the other one is physical design task. So circuit design task means this can specify the performance of the primitives, what are all the needs. And physical design task means this can generate mask geometry. So here the characteristics of analog design is examined at the system level and the cell level. So the first approach is divide and conquer hierarchical decomposition. So here the design is breakdown into sub-designs. So see here, for example, so this is analog system design process, how we are doing decomposition into sub-designs. So this is mixed signal system concept. So first the architecture splits into sub tasks and the evaluation is done. Then inside the architecture we can go for decomposition into circuits and we can do evaluation, and from that we can go for layout, then again we can evaluate. So here the major design is decomposed to the lower levels, decomposition of system into lower levels. So here all the sub-design tasks are proceeded without any information about the result. So they can proceed in parallel. They are not bothering about the result from the other sub-design task. So they can proceed in their own way. So this method is called divide and conquer. Then here the information about the other sub-design tasks is required if we go for measuring the quality. So if the information about the other sub-design or task is less known, then the better will be the hierarchical decomposition. So here you can say for example a Miller compensated unbuffered op-amp decomposition. So there is a transconductance amplifier, current mirror and differential pairs. So the first decomposition is with these, then it can again decompose into the first stage and the second stage. So here if the knowledge of the first stage is not known, then the knowledge, the decomposition of the other one is a difficult task. We are unable to decompose to the next level. So the decision making is not possible without the knowledge of the other subtask. Then the next one is system level analog design. So this is one of the example where pipeline A to D converter, how the hierarchical decomposition is done with this. So the first single stage, stage 1 and stage 2. Again, this can be split into the op-amp and the related capacitors and switches. And here stage 2 is again decomposed into the comparators, op-amp and switches. So the pipelined A to D converter is first broken into the number of stages, whatever may be the number of stages, it is broken down into number of individual stages. Then each stage is again decomposed to a comparator, op-amp and switch. Then again it is decomposed, right? Then it moves to the end component. So whatever may be the final component, see here op-amp, switch and comparator. So these are all the fundamental cells. This is the end stage. We are not going to do the further decomposition from this, these are considered as the fundamental cells. Then the next one is cell level. For example, here CAD tools for digital ASICs are used. Here these tools are based on the hand designed and optimization cells with the basic digital functions like gates. Then simulation based analog cell design. So these are based on circuit simulator in order to predict the performance. Then equation based analog cell design. So this is used to predict the approximate behavior of both analog circuits and devices. So here this equation based method successfully do the synthesizing without requiring any starting point information. This is very, very important. So in the equation based analog cell design, we are not in any requirement. Without any starting point, you can do synthesizing analog circuits with the equations. The next one is hybrid approach. So here the tool used for hybrid approach is asterisk and this OBLX. So here the hybrid approach is derived from the previous one, equation based. So without any information, starting information, we can proceed. With the equation based method, two modifications can be incorporated. So here the requirement is only simulator device models. Then in order to decrease the number of equations, we can the expert designer provide, particularly the ones that are difficult to derive. So here in order to reduce the difficulty to the designer, the number of steps for the equations in order to get the equations is decreased here by means of this hybrid approach. When working with the equation based, we need complete mathematical equations, right? That is very difficult to derive. So when going for hybrid approach, that is not needed. The entire derivation is not needed. The number of equations can be reduced. Then the VLSI technology trend. So frequency and power trend, scaling. So when working with the scaling, transistor scaling, interconnect scaling, then capacitive and inductive coupling and leakage. So these are the major factors related with the scaling challenges. So we will see few comparisons. So this is a processor frequency trend. So in 1987, you can see this is a frequency in megahertz. So you can see the frequency. So for each generation from here, Pentium, Pentium Pro, Pentium 3, Pentium 4, for each generation, the frequency doubles, right? So this axis represents gate delays and clock. So here, the number of gates per clock reduces by 25%. So the red color line shows gate delays per clock. So this reduces by 25%, whereas frequency doubles for each generation. So here the frequency, processor core frequency, and the bus clock, core clock and bus clock. So the yellow color shows core clock and the red color shows bus clock. So the bus clock is the frequency, clock frequency, bus clock frequency is lesser when compared with the core clock, right? So this is a comparison where bus frequency is not that much high as that of your core clock frequency. Then power density trend. So the leakage power, the power density for 0.25 micro, 0.18, 0.13, 0.1. So here all the calculations are based on the assumption that the die is 15 mm and 1.5 times the frequency increases per generation. So here the leakage power goes on increasing and the active power also rises, but the leakage power increases here to the maximum when the size is getting reduced. Die size is getting reduced. Then the next one is voltage scaling. So here the supply voltage reduces, and nowadays we are working with less than 1 volt. So the next one, transistor physical gate length. So this shows the technology node, the red color, and this shows the physical gate length of the transistor in microns. So if we consider this physical gate length with this technology node, we can say, for example, see here the physical gate length is in 19 up to this 1997, 1995, both the things are same. After that, the transistor physical gate length is this, and the technology node is this. So if we consider this, for example, then 70 nanometer length gate NMOS transistor is given here using 0.13 micrometer technology. And this is a research transistor with 20 nanometer physical gate length using 45 nanometer technology. So 45 nanometer technology, so the width and length, so 20 nanometer, 40 nanometer. Then oxide thickness scaling. So the thickness goes on decreasing. Here this shows the oxide thickness, and this shows the equivalent physical thickness, oxide thickness in nanometers. So if the technology generation goes to, for example, with the previous, we are working with the 0.13 micrometer technology, right? So with that, what is your oxide thickness? So if we are going for 0.1 micrometer, the oxide thickness is less. So the technology generation is moving towards 0.1, 0.07 like that. Then the oxide thickness goes on reducing. So for scaling, we need to reduce the oxide thickness, right? So it is goes on decreasing. So SRAM cell size is also getting reduced. So this is cell size in square micrometers, and this is technology generation. So with the 0.13 the SRAM cell size is reduced to 2.1 square micrometer. Then the number of metal layers goes on increasing with 1.5 micrometer technology. It is with 2 metal layers, but with 0.13 micrometer technology, it is with 6 metal layers. So the number of metal layers goes on increasing with the technology generation development. Then this shows the power efficiency, memory power efficiency. So the red color dotted line shows the memory power efficiency. So the technology generation development shows more power density, but here the logic occupies more power, utilizes more power when compared with the memory. So lower leakage when compared with the logic circuit. So this is in terms of tens, whereas this is in terms of hundreds. Then interconnect RC delay versus pitch. So here interconnect RC delay, and this is pitch in nanometer. So we can say with the different materials, copper and aluminum, and with a different technology, how the interconnect delay is minimum when we are going with the interconnect pitch. So here the pitch is in hundreds, so we can get the delay with 120. If we are going for the pitch size of 1500 nanometers, we can say the interconnect delay in terms of a minimum within tens. Then the next one is noise sources. So here capacitive coupling and inductive coupling plays the major role for noise. So here due to electric field and due to near field effect, and measures the resistance to voltage change, we can able to get noise due to capacitive coupling, and due to magnetic field and far field effect, and measures resistance to a current change and frequency dependency, we can say inductive coupling occurs, so that noise is possible in the circuit. So here with the conclusion, with all these discussions, we discussed so far what is analog IC design, what is mixed signal VLSI design, and what are the drawback with the analog signal processing. And with example, we discussed mixed signal, then various scalable process and a comparison between analog and digital basic building blocks, and the challenges, what are all the design tools available in today's scenario, then what are all the testability methods for analog circuits, then what are all the fault simulation methods, and how can we improve the controllability and observability in analog circuits, then what is the meaning for scan technique in analog circuits. Then we discussed about CAD tools for analog, what are all the methods, then what are all the trends. So you can now get a clear idea about the challenges and the trends. What are the possible the major drawback of analog signal, analog design is testing. So testing plays the major role, so that we have discussed so many methods which are available for analog design, and what are all the automation tools available for conventional systems, and what are all the design tools available in today's scenario. So based on these discussions, what I want to convey is scaling is expected to continue for the next 10 years possibly. So if scaling is the possible way of research, then the analog designers should focus on the scope of variables, on what they have to give attention, and what they must manage, and what are all the circuit constraints, and how better their analog design is. Because as per the discussion, even the system has a small analog module, then that simple part decides the performance of the overall system. The entire system is digital and only a small part is analog. Then that analog part decides the overall performance of the system. So the quality of result, how better the analog design is very important. And the designer should give more concentration towards the variables on which they have to manage, and what are all the circuit constraints. So these are the things on which the analog designer should focus. The analog design is difficult because of these things what we have discussed. One should know about the working of analog design as well as the digital part of the design, and the conversion process, what happened to the system if we integrate these two. So the integration also creates many issues. So the interdisciplinary knowledge is necessary when working on this analog design. So with this, I want to conclude the session. So if you have any query, you can post.
Dear participants, if you have any doubts or queries, you can ask now. Ma'am, there is a no more queries from participant sites.
Okay, sir.
Let me conclude the session, ma'am.
Okay, we will finish the session, sir.
Okay. When educating the minds of our youth, we must not forget to educate their heart. In this way, I would like to thank our today's resource person, Dr. V. Geeta, Department of Electronics and Communication Engineering, Congo Engineering College, for providing the wonderful session on the topic of design of switched capacitor fuses and the role of analog signal processing in VLSI and trends and challenges. Thank you so much, ma'am.
Thank you, sir. Thank you for the opportunity given. I want to convey my thanks and regards to the management of Kongonadu Engineering College and the principal and the coordinators for providing me an opportunity to share the knowledge in analog signal processing domain. Thank you.
Thank you, ma'am. Sure.
Thank you for the opportunity given.
Dear participants, the day to session 2 attendance and the feedback link is posted in chat box. It will be open up to 30 minutes only, so kindly fill it soon. While filling the feedback form, kindly choose your respective FDP ID. Thank you all. Dear participants, at the end of this FTP, we will share all recordings to your registered mail ID. Thank you all.